What makes some APIs become DSLs? By the end of this episode, we'll have a good explanation of the power of DSLs and the thin line that divides them from ordinary APIs. Hello, my name is Eric Normand, and I help people thrive with functional programming. So I was reading the stratified design paper a few episodes ago, and I've also asked myself this for a long time: where does the power of a domain-specific language come from? Why is it something that seems to have some kind of transcendent property? It gives you this leverage, this huge amount of leverage. You go from a low level to a high level very quickly. And it seems that there's a lot of discussion online, meaning in blog posts, essays, people trying to come to grips with what's the difference between a normal API and a domain-specific language, a DSL. And I think after reading this paper, I have a really good answer. It's, finally I figured it out. So I'm going to share my idea here, and I think it's a good one. Of course, in all humility, I know that other people have thought a lot more about this than I have, and a lot smarter people. So please point me to other explanations of this. But I think this is it. Okay, so let's imagine an API, just like a normal API. And let's say it's for drawing graphics. So this API might have a function or some method on it for setting the color of a pixel, or drawing a square, or drawing a circle and changing the color, those kinds of operations. And you could look at the docs and you feel like, okay, this has a logic to it, and I can kind of figure out how to draw whatever I need to draw, right? But it doesn't feel like a domain-specific language. It just feels like I have these commands I can run, and that's it. I just have to figure out how to turn them into a sequence of commands that will draw what I want it to draw. But a DSL feels a lot different. So a DSL would be something that would let you describe the picture that you want drawn, not as a sequence of actions, but in some other way that feels much more expressive, and like your I don't want to use the word declarative. I have a whole episode on why I don't like that word, but you just feel like it's much more expressive. Now, in the paper Lisp, a language for stratified design, the authors talk about two things that I think are very important for like what causes this difference. This DSL, it is an API. It is a way to interface with this code, but it somehow feels more expressive. And why is that? There's a line that you cross at some point. Okay, so I'm going to try to back up and describe these two properties of languages of the stratified design that cause it to cross that line. People have talked about this line. They talk about, oh, it's some intuitive line that you kind of cross, and I know it when I see it. But this does a much better job. This paper does a much better job of giving the actual principles in it. Okay, so we have to look at what is a language. And in structure and interpretation of computer programs, and it is repeated in this paper called Lisp, a language for stratified design, the authors define a language as consisting of three parts. There are the primitives. This is the stuff that the language gives you. There are the means of combining Okay, means of combination. That's taking things in the language and putting them together to form new things. So this might be writing a function or building up some other thing like a class. And then there's naming, which is where you give something a name so you can refer to it later. And that naming can give it a higher meaning. Okay, and so they define stratified design using these three terms. So you have, let's say you have 3 layers. Usually you have more, but let's just focus on 3 layers. So you have layer A, and it defines some things, right? Whatever, doesn't matter. There's some things defined in that layer. Then on top of that, you got layer B. And it uses the things that are defined in A, right below it, as primitives. So you have one, that's one of the principles, or one of the 3 things that a language needs. So it's got the primitives. Then it defines new means of combination of those primitives. So this layer B is now defining means of combination. That's number 2. And then and then it names them, so that's 3. And then layer C can now use stuff from layer B as primitives. So each layer is actually a whole language. That's what the paper is trying to say. Each layer is a language built on top of the layer below it. So it's like a stack of languages. Okay. Another thing they talk about in the paper is what's called the closure property. That's closure with an S. I know I talk about closure with a J a lot, the programming language. This is closure with an S, the actual word closure. Now what this is if you have a function that returns the same type as it takes as an argument. So for instance, addition takes 2 numbers and it returns a number. Multiplication takes 2 numbers and returns a number. String concatenation takes 2 strings, returns a string. Okay, all of these operations have the closure property, right? So what that means, though, is that you can arbitrarily nest the expressions. So you can put a plus inside of another plus, inside of another plus, inside of a times, because it also participates in this numbers to numbers thing. So the reason why addition and multiplication feels so expressive, like I can do anything with these and I can express any combination I want, the reason it feels like that is because of the closure property. It allows them to be nested, and so you can have recursive expressions. Okay. So what this means, though, is then you have like an infinite number of possible expressions. Once you have recursion, you don't have to just get longer, you can get deeper to express what you want. And this is where I think the line is. It's when you have a DSL, you've actually crossed this line of having recursive expressions. So some people might say that the string API, you know, the standard string API is an API where you can concatenate strings, you can get substrings, you can search for a string within another string given a regular expression, you can repeat strings, etc. Or you can trim, right? Notice that all of these take a string and return a string. So one thing you see is that these can be chained arbitrarily, and that's very expressive. You can nest them arbitrarily. So I can concatenate this weird expression of strings with this really complicated expression of strings. I can concatenate them together and get a new string. And so the reason it has crossed the line is because you're always dealing with strings. Once you have a string, you have an infinite number of things you can say. And this is different from if you say it didn't return the string. Say it just modified the string. The only thing you could do is sequence them. So you could get a longer and longer sequence of commands, but you couldn't get that infinite nesting, that recursive property, which allows for these really complex and intricate ways of combining them together. Well, I think that's it. I think that's the line right there. I don't know what else to say about it. I can just give a bunch of other examples. So an example of something that we chain a lot in functional programming is like sequence operations, map, filter, reduce, etc. Notice they all take a sequence and return a new sequence, except for reduce. And then reduce kind of ends it, right? At the end of a chain, you might do a reduce to like sum the things up or average them or what have you. But then you're done. There's no more to do. So the reduce does not have that closure property. But map, filter, all the other ones, like the opposite of filter, which does remove, something like repeat or cycle, all these sequence functions, sequence operations that take a sequence and return a new sequence. They have this closure property, and that's what allows them to be richly nested and chained in basically infinite ways. And it's what makes it feel like a DSL. It feels very expressive. So this paper was, written so long ago. Like, it's crazy that we haven't, like, in all these online discussions, this never comes up. People just talk about it like I know it when I see it. But I really think this is what it is. It's all about the closure property and nesting. And, well, I think I'm going to end it there. So let me give a quick summary. I've heard that people really like my summaries. So I've been thinking about this question for a long time. What is the difference between an API and a DSL? And I think the paper Lisp, a language for stratified design, which I read and reread carefully for this podcast, it finally gave me this insight into what it is. Obviously, it's not my idea, but I'm kind of applying it to this question that was in my head, and this is the answer. So in the paper, there are three things that define a language. There are the primitives, the means of combining things in the language, meaning you can combine primitives, but you can also combine the new things you've created by combining the primitives. And then there's naming. So that's three things: primitives, means of combining, and naming. Naming just lets you put a name on something, give it a little human level meaning, and refer to it later by name. Stratified design is where you build a language in each layer on top of the layer below it. And then the closure property is where a function takes a certain type of argument and it returns that same type. And if you have a collection of these, then they can all kind of participate in nesting with each other. And if you get enough of them, you get this nice combinatorial explosion of the expressivity that you can do. One thing that I didn't mention is there's in a previous episode I talked about what is complexity, and I kind of concluded that this is in my response to Out of the Tar Pit. I concluded that complexity is the nonlinearity. It's not that complexity is nonlinear. It's the complexity is the nonlinearity of a system. So something like the number of possible interleavings of two threads. The longer the threads are, the more possible interleavings. It's factorial, right? So it's nonlinear. And it just explodes, and it makes it much harder to understand what the program might do. And notice we've got an opposite thing. We've got a complexity, meaning a nonlinear way of combining these things. We don't just add to the end. That would be linear. But the nonlinearity is that we can nest deeply. And now we've got this combinatorial explosion of the kinds of expressions we can do because of the closure property. Every new function you add into that ecosystem, every operation that takes a string and returns a string, boom, now it just increases the different ways that multiplies the different ways that you can combine them. And so this is a positive complexity. It's a positive nonlinearity. It opens up doors that the programmer can use without adding that much difficulty to the system. Notice you add one more operation, but it is multiplying, maybe even factorial of the number of possible expressions that you can do. So you've got this linear increase in code size, one more function, but this huge multiplication of the number of possible expressions. So, I mean, I'm kind of bringing this into kind of compiling this up into a theory of complexity, and like good types of complexity, bad types of complexity, complexities that help the programmer, complexities that hurt the programmer. I'm not really sure where all of this is going, but if you have a complex domain that does seem like it's super open, such as graphics, then perhaps the way to make graphics possible to try to tap into, there's infinity number of paintings, right? There's no limit to the number of paintings. And so somehow by defining a language, a DSL, instead of just an API, you are better able to tap into that infinity, right? You're never going to be able to express everything with any particular DSL, but imagine having to use an API where the only way you could increase the number, or so the only way you could get to another type of drawing would be to add to the end of the program, right? Or add somewhere in there. So you just increase the length. There's no nesting. So you have this like linear increase in the number of lines of code, which gives you linear, access to linearly more paintings, right? Because you could choose what that line of code does. It just gives you like a little bit more choice. Versus you can arbitrarily nest them. This gives you a much richer set of choices. So a linear increase in your code size will open up a huge array of the type of paintings you can do. Obviously you can't get all of them because there's going to be certain assumptions baked in. Like for instance, you might only be able to draw rectangles, right? And you don't want like the paintings might not even have rectangles. There's the paintings with zero rectangles in them, and so you can't paint those. But you can paint an infinite number of paintings with just rectangles. So you would have to come up with a different DSL to let you paint something else. But you are better able to spread out and have a wider range of possibilities with only that linear increase in length. Okay, this is pretty exciting. I think that there's something there, and I want to keep following this vein. So if you want to listen in as I ideate, as I figure this stuff out, you can go to lispcast.com/podcast, and you'll find links to subscribe and reach me on social media. Part of the reason I'm doing this is because I like to be part of the discussion and reach more people, so that if this does strike a nerve with you, you send me an email or something and we get in a real discussion. So it's still me, it's still people and people. That's what social media means. It means it's people. It's a media made out of people. But I don't like to look at it like broadcast only. It's definitely good to broadcast, to get the idea out there and touch a lot of people, have contact with a lot of people. But the reason you have contact with a lot of people is to make one-on-one connections easier, more efficient, right? Because I can't contact 1 million people one at a time linearly. So a linear increase in my time expenditure gives me a linear increase in the number of people I can contact, and they might not be interested in this topic, right? So it's a big waste of time. But you can do like a broadcast. It's linear increase in the time to record this and post it, and then a potentially exponential increase in the surface area of the people I touch. So and then can initiate conversations with. So please look at it that way. This is a call to you, the dear listener. If you are hearing this and you like this topic, if you are curious, please reach out. You'll find links to email me or get in touch with me on Twitter right on that site, lispcast.com/podcast. Okay, so my name is Eric Normand, and this has been my thought on functional programming. Thanks for listening, and rock on.